So we have a lecture today, review on Wednesday, and test on Friday is the way I recall things. And I'm going to stick with that schedule, which means we won't cover quite as much physics because I don't want to cut into the time for the other topics. It's not just a physics course, even though physics is the thing I love. So today we're going to talk about electricity. And so we're going to talk about electric force. And to introduce this, remember on the test, one of the things that you're going to have on that test is you're going to have to name the simple four-step scientific method that we've talked about, and then you're going to be given the situation you're going to have to apply it. So I'm going to do something to simulate that process here. So what is the first step of the scientific method, what you're going to put down on the test? Right. Scientific, it's got another. One, observe something interesting. Now you're also going to be given an observation and you're going to have to go through. What's step 2? Okay, create a hypothesis, and that hypothesis has to do 3 things. Explains why the observation occurred. Right? If it doesn't explain anything, it's not useful to us. What else?
Has to be testing that.
Has to make testable predictions. And what's the final thing? Based on science. I put scientific knowledge here. You could put based on science. Needs to be something that is based on science, shows a causality. So when we talk about things like astrology takes scientific information. Where we observe the sun and the planets in the sky, that's scientific information, scientific knowledge. Where does that fail? It fails in that it doesn't make testable predictions because there's no connection that you can draw between that scientific information and the predictions that people make for astrology. So let's take this here. I have I'll take rubber rod. This here used to be fur of some kind. It's, I think, sheep originally. Now it's just, it's kind of like it's been fleeced now. Anyway, so I rubbed this stuff up, and people noticed long ago, they rub something like this, and interesting things happen. Like, I'll bring it up to this little pith ball, and you see it's pushing it away. Now I touch it, and it does crazy things. Now it's moving away even more. That's something interesting, right? So the observation here is rubbing a rubber rod on wool makes it so it puts a force at a distance even, didn't have to be touching, on the pith ball. Okay, so that's actually styrofoam, but traditionally we use pith balls. So that's in something interesting. The next step, create a hypothesis that explains why this occurs based on scientific ideas and makes testable predictions. why do you suppose when I rub this thing on the fur, it would do this funny stuff? Static means stationary, so I need more than just that word. Static what?
Friction.
Not friction here.
Static. Jumping.
Static electricity.
Okay. Now, static electricity is the right answer, but at that point, when people first discovered this, they didn't even know electricity. So they had to go to other ideas that are more basic. Things like, well, because it makes that thing move, what must it be doing? I didn't hear you. Force. It must be putting a force on it at a distance. Well, at this point, we know force is like the force normal that's pushing me up out of the ground. That's not what it is. We know about the force of gravity. That's not what it is, because gravity doesn't change when I rub something. So it must be some new kind of force. And of course, based on already you said static electricity, we know now that that's electric force. But back in the early days, you got to start playing around with things. So you make predictions like, okay, so if this pushes away, maybe it always makes a repulsive force because of, and you got to come up with some idea of what causes the force. So we'd say, well, something that's on here, something that got rubbed on here or rubbed off of here. Now, something we can do here as kind of a test is this here. This is two pieces of metal. And when I bring this up, you can see that it's making something happen even though I'm not touching. Take it away, it's like it was before. I'm going to put on here and rub it. And now it's permanently doing something. So I'm just exploring here, but I can see, wow, if it's permanently doing something, what had to happen? I had to transfer something. Now I'm going to rub this some more just to make sure it's got whatever it started with on it. And bring it up here. And when I bring it close, why it just goes further, right? Now, one of America's great scientists did a lot of work on this. You guys know who that great scientist is, Benjamin Franklin. And one of the things that was noted at the time of Benjamin Franklin, so now I'm taking a glass rod instead of rubber. And if I bring this up, it gets smaller when I brought this one up. When I brought the rubber, it moved farther away. Brought this one up, it moved the other direction. And so determined, well, there must be two types of things going on here. Because we rub something onto this, and this has the opposite. And so Ben Franklin said, whatever we have on this after I rub it, I'm going to call negative charge. Charge being just, whatever's doing, whatever kind of force it is, and we call that force electric. And whatever I had on this is positive charge. And when Ben Franklin was doing his experiments, instead of rubber, he was actually using amber. And the Greek word for amber is electron. And it turns out that the extra things that are on here are now what we call electrons because of the amber rod for those experiments. So what we find from simple experimentation is there are two types of charge. And so I went through a lot of talking here on the create a hypothesis part and doing some experimentation. But the hypothesis is, there is a force associated with something being rubbed on or off. OFF. Does that make sense? And so, Ben Franklin just, arbitrarily basically set that electrons were negative by making a hypothesis like this and then doing testing. So, is this based on scientific ideas? Well, it says there's a force associated with something. We don't know what that something is. It's not a complete knowledge. But a force, that's definitely a scientific idea. And does it make predictions? Well, yeah. Because if it says that there's a force, we can test how strong the force is. If it says it's something being rubbed on or off, then we can test about that rubbing on or off. So it's making testable things that we can do to explain what's going on. So that's a perfectly valid situation. What's step 3? Test. That could disprove the hypothesis. So a test that could disprove my hypothesis here, there's a force associated with something being rubbed on or off. So I might say, okay, well, I could test this and maybe measure the mass of my rod. And if the mass of my rod changes after the rubbing, then that would agree that something was rubbed on or off. If it stays the same, that would disagree, right? So that would be a test. Now, if you and I were to do that test, it would fail. Not because the hypothesis is wrong, but because the actual mass of the things that are being rubbed on or off is really, really small. We wouldn't be able to measure that unless we had really, really, really precise instruments. But that's a test that could be made. And historically, we have things like that happen, that people do a test, and the test says, ooh, it's wrong. And it turns out it's because the test was the part that had the problem. An example where we know we have tests that invalidate theories, and yet people believe that the theory is still right and the test is not sensitive enough, is talking about gravity. Gravity, we learned Newton's law of gravity is proportional to 1 over the separation squared, right? Well, that 1 over separation squared is because we live in a world with 3 spatial dimensions, right? Up, down, left, right, forward, backward, 3 mutually perpendicular directions. You can't make a 4th direction that's perpendicular to all 3 of those. So that's why we're a 3-dimensional world. Well, there is a theory that says that we actually live in a world that has 7 more spatial dimensions. So a total of 4 plus 7 is 11. But the other dimensions are really, really, really tiny, so we can't perceive them. And if that's true, then the inverse square law, the force of gravity is 1 over distance squared, should change if you get 2 things really, 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 really closely. And so experimenters have done experiments trying to measure a change in that equation for the force of gravity if they get things really, really close. And so far, the results have all shown there's no difference, which violates the theory. Except they say, well, we're not getting them close enough to be able to measure the deviation that the theory should introduce. So they still hold on to the theory because the evidence isn't testing enough. So we go on, we conduct that test, we measure the mass, it fails. What do we do if it fails? We go back and we change the hypothesis so that step 4 is if it fails test, change the hypothesis to include the new information. So if my test here was measure mass of rod before and after rubbing, and compare, because I know the outcome of that is going to be it fails, then we'd go back and we would change the hypothesis to include the new information. So being a stubborn person, especially in hindsight of knowing what the actual truth is here, I'd go back and change my hypothesis and say, okay, I still think that I'm rubbing something on and off, but it's something that's very, very low mass. Right now I modified my hypothesis so that that experimental result is now in line with my hypothesis. And then I would go through and create a new test that could test my theory in a different way. What if it passes the test? Then you test a new prediction or test another way. And that leads to part of the frustration of the scientific method is you never are done. You never can say, I proved it. All you can say is I've tested it extensively and have found it to be consistent. And after doing that many, many times, we start to develop a lot of confidence. So everybody, in physics at least, believes in gravity, the force of gravity that makes things fall. Even though conceivably there might be a test that no one's ever thought of that could prove that it's incorrect. Because you can prove things wrong, you just can't prove them right in science. So now I know that we have a test coming up, and that's something that will help you on the test. So this electric force is a new force. So before we had one fundamental force that we've worked with. Gravity is the one fundamental force we've worked with. Now we have a second fundamental force, the electrostatic. Actually, let's go with electromagnetic force. And this electromagnetic force is very, very important. Everything that we interact with on a daily basis, things like this table, how I stay to the earth, it involves one of two forces, either the gravitational force or this electromagnetic force. Every single thing you interact with. Physicists are aware of two additional forces, but those two additional forces only act with things so close together, like in the nucleus, that anything you normally interact with, it's not involved. Now you could say, oh, but the atoms I'm made up of, the atom nucleus itself is held together by those forces. Yes, it is, but you're not interacting with the atom's nucleus. So the force that keeps me from falling through the floor, what do we call that force? The normal force. The normal force is the result of electromagnetic forces holding molecules and atoms together. And because of that electromagnetic force that won't let them move apart, when I push down, it holds them together and makes the upward force to keep me from falling through. So normal force is really an outcome of this electric force. So based on the work of Benjamin Franklin, we have negative charge with electrons as the fundamental particle. And we have positive charges with protons as the fundamental particle. And it turns out the charge, right, the charge is, think of it like mass. Mass tells you how big the force of gravity is going to be. If I double my mass, I'm going to double the force, right? Charge is the same thing, but it's talking simply about a different force. It's electric charge, whereas mass would be gravitational charge. And so if you double the electric charge, you're going to double the force. Just like if you double the magnetic charge, you're going to double the force, or not magnetic, the gravitational. In fact, Charles Coulomb, I think it's Charles, came up with a law that says the force between electric charges is equal to a constant. K just means constant. In this case, that K is equal to 8.987 times 10 to the ninth newtons times meters squared per c squared, which I will introduce in just a moment. K times charge 1. We use the symbol Q for charge. Actually, I'm going to change the color here. Times Q2 divided by the separation between them squared. That should look familiar. That's exactly like the gravitational law, Newton's law of gravitation, except for instead of capital G, we have K. But they're both constants. And instead of mass 1 times mass 2, we have Q1, charge 1, times Q2, charge 2. And then it's divided by the separation squared again. So this means electric force, it gets bigger if you increase the charges. It's proportional to the product of two charges. So if I have a charge of, let's say, plus 2 protons, and let's say Vanessa has a charge of 0, what's the product of my plus 2 protons and her 0? If I multiply them together. 0. How strong then is the force between Vanessa and me in that situation? Because the product of Q1 times Q2 is 0, what's the force going to be? 0. So the electric force only acts between things that have a non-zero charge. If something has a 0 charge, that means it's not affected by the electric force. If it has a charge that's something other than 0, it is affected by the electric force. Just like with mass, if something had a mass of 0, a photon has a mass of 0, then it's not affected by the gravitational force. If it has a mass, it is. But something that's different is mass was what we call unipolar. Everything has a positive mass. Nothing has a negative mass. And the force of gravity is always 100% attractive. But with electric charge, we saw that it comes in 2 types. So we call them positive and negative charges. And if we have 2 positive charges, they will repel. That is, 2 positive things will push each other apart. If we have 2 negative charges, they will also repel. They'll push each other apart. But if we have opposite charges, one positive and one negative, then they attract. So we have that common saying that is a physics saying, opposites attract. Because opposite charges, a positive and a negative charge, they attract. But likes repel. So if we have 2 positives, they push each other away. 2 negatives, they push each other away. So when I came back to this, based on that information, because of my amber rod, I rub it, it's going to have the same type of stuff rubbed on that it had before, right? I mean, it should. There should be no reason for it to change. So I bring it over, it should push away, it should repel because they're the same thing, and likes repel. But if I do the glass rod, it's going to be the opposite charge and opposites attract. So instead of pushing away, it pulls it back. Now, a couple more things. The actual size of the charge. Because it's Coulomb who did the experiments, we name the charge unit after Coulomb. And so it's called coulombs. Yes, ma'am?
When you're rubbing the glass, you rub it on your shirt and nothing moves. So that means, does that have a difference on whether it attracts or?
Okay, that's a good question, good observation. She noticed I rubbed it on something different. As we understand things today, you have electrons on everything. Atoms are made of a nucleus that has a positive charge, it has protons and neutrons in it. And then they have electrons that are orbiting around them. And those electrons there's a certain force, an electromagnetic force, holding the electrons to the atoms. And some materials will hold the electrons with greater strength than others. And so when we're rubbing them, we're rubbing something that holds electrons. This one here really wants to hold on to electrons. This not so much. And so what's happening is the electrons are coming off of this and going onto this rod. And so by doing that rubbing, this here, if it loses electrons, if you lose negative, what do you become? Positive. And you can think of that in finances. If you have debt, that's negative money, right? And if you lose the debt, if it's forgiven, you didn't pay any money, but you just got more wealthy, right? You went up because you lost negative. And of course, we can also see the opposite. And so this became positive because it lost electrons. This became negative because it gained electrons. Now, when I changed to using the glass, like I said, different materials have different strengths they want to hold on to their electrons. And so I used the glass here and rubbed it on something else that would be more attracting electrons than the glass, so that I would move them onto my shirt and off of this to make it positive.
So if you were to rub them onto the metal, would it still be?
Well, we can do the test, right? I mean, that's what science is all about. You got a question, you do the test. The truth is it can go either way because it depends on the 2 materials. Okay, so which way did it go? So this was positive whether I rubbed it on the fur or whether I rubbed it on my shirt. But at least in theory, it should have been a little more effective at making positive rubbing on my shirt. So that's good inquisitive mind, the thing I'm looking for. So the unit of charge, the Coulomb, named after a person who experimented with Charles Coulomb, person who came up with this equation right here. And so the charge of an electron, one electron has charge of minus 1.602 times 10 to the minus 19 coulombs. 10 to the minus 19, what does that mean to you? Very, very small. There are two possible answers people would have said. Nothing, because they're not sure what 10 to the minus 19 means, or very, very small. 10 to the minus 19 means essentially 0.18 zeros and then the number that follows. Right? One less than 19 is 18. So that's a really small amount of charge on an electron. A proton has a charge of 1.602 times 10 to the minus 19 coulombs. What's the difference between the charge of an electron and the charge of a proton? One's positive, one's negative. Proton, the pro means positive. Electron, well, electron just it's from the Greek word for amber. So here's reminding us of the fundamental rule. Things that are the same, like charges repel. Down here we have opposites attract. So this here is important because what's our next topic after the test? Chemistry. And so in chemistry, we're going to start out, chemistry is what used to be a field in physics that became so large that it got branched off. And chemistry is looking at the forces between the different atoms that have a nucleus that has some positive and some neutral things, and then electrons going around. So out here we have electrons, and then here we call this thing here the nucleus, and we have protons are the positive things in the nucleus, and then we have those neutral things, and those neutral things are called neutrons because they're neutral. Now, what should the two positive... This here is a helium nucleus, by the way. This is a helium-4 nucleus. What should those two protons in the nucleus be doing to each other according to the electrostatic force? They should be repelling each other. And yet, that is one of our most stable nuclei. I say one of our most stable. It's quite stable. When you have radioactive decays like uranium decays, oftentimes it shoots out a helium nucleus. That's why we have helium in our atmosphere. The Earth can't hold on to hydrogen or helium gases, but hydrogen and helium gases are both created in radioactive decays. And so we're replenishing our hydrogen and helium, which is why we still have those gases, even though we can't hold them. So why are they held together if they should be repelled? That's where the other two forces come into play. The strong and weak nuclear forces are the ones that are responsible for holding the nucleus together. And we will never discuss the strong and weak nuclear forces other than to say that they exist, and that's why we have nuclear power to begin with. What about the electrons? How should the electrons feel toward the nucleus? They should be attracted because opposites attract. Why don't the electrons fall into the nucleus? They're too busy repelling each other. There is going to be a repulsion between the electrons, but that in and of itself doesn't explain it. Did you have an answer, Justin?
No.
Well, just like, why doesn't the moon fall and hit the Earth? What's the answer?
It's moving fast enough.
It's moving fast enough to keep going. And so it's falling in, but never getting closer. Well, the electrons should be doing something like that. I say should be. And we'll go through this later, but scientists have gone through a lot of hypotheses that they had to scratch because of experimental results that disagreed with them. And so the earliest model of the atom was that you just had, and this is where the word atom comes from. It comes from the Greek for indivisible. Democritus, I think, came up with the idea that if I take something like this and I cut it in half, I'll have two smaller pieces. Shocking. If I take one of those and I cut it in half, I'll have two even smaller pieces. And I keep going and dividing it. Eventually, I'll get to some point where I can't divide it anymore. And so he said, I'm going to call that smallest piece that's indivisible an atom that means indivisible. So that's the earliest understanding. Well, then we had experiments that showed that there were electrons in matter. That there's electrons in, for instance, this tabletop. Or, as Lev would have, the actual experiment they did was with metals. And so they said, oh, well, if there's electrons in the materials, then we must have something, and they call it the plum pudding model, where we have a bunch of just mushy positive charge spread out everywhere. And then we have like little raisins that are the negative charges of the electrons. And so, they started with just an idea that Democritus proposed, but then when they found new information, they had to modify it because it no longer worked. But then with that new information, the new idea, we have the very famous Rutherford experiment. Ernest Rutherford was a high-level physics researcher, and working in his lab, he had Geiger. You've probably heard of a Geiger counter, right? That'd be Geiger's thing. They were studying radioactive materials. And then they had young Marsden who was working in the lab. And Geiger said to Rutherford, I think Marsden's ready to do his own experiment. And so Rutherford says, okay, we understand that material is made out of just a positive mush everywhere with these little points of negative charge. So let's take ourselves a piece of gold, and gold is malleable. That means you hit it with a mallet, instead of shattering, it squishes, which is why you can make gold leaf on things. So let's just pound a really thin sheet of gold, and then let's shoot helium nuclei at it, the things right there. So they're going to shoot helium nuclei. So 2 protons, 2 neutrons are going to be shooting at this at high speed. And there might be some little negative that it hits, or it might miss completely. Now, they knew that the mass of an electron was way, way, way smaller, like more than 1,000 times smaller than the mass of that helium nucleus. So based on their understanding, what should happen to the helium nucleus, we call it an alpha particle, by the way, if it hits the electron?
Stuck to me.
Well, let's take it into things you understand. I've got a bowling ball, and there is a BB not sitting on the lane, but just at the same height as the center of the bowling ball as the bowling ball rolls down the alley. The bowling ball hits the BB, what happens? The BB goes flying, does the bowling ball bounce back at you? What does it do? Keeps going with just a very imperceptible decrease in its speed, right? So expect the worst case scenario, the alpha particle slows down just a wee bit. If it comes close and doesn't hit the electron, there should be some attraction because they're opposite charges. It should be change, deviates path just a tiny amount so it doesn't go perfectly straight through. So that's the outcome they expected. So, scientific method, they're now going to test their hypothesis. I mean, this whole experiment was testing the hypothesis of what they called the plum pudding model. Plum pudding is the general positive charge spread everywhere with the little electrons, the little raisins of negative charge. So they did this, and what they found is most of the alpha particles went through, no slowing down or nothing, just went straight. But some of them bounced straight back or at crazy angles. Now, when Rutherford went on the tour, going and talking about his great physics, because who wouldn't come to hear a great physics talk, right? You would all do that, right? Pay good money for it, right? I didn't think so. So when he goes and he gives his talks, he said, to us, it was like if we took toilet paper or tissue paper. Right? Probably didn't use toilet paper back then, right? We took tissue paper and we spread it out and we fired a cannonball at it. And instead of going through the tissue paper, it bounced off the tissue paper, right? I mean, because they believe this wholeheartedly. But their experiment said, no, that ain't no tissue paper. If it bounces back, it has to be the reverse of what we said. We had to have had the bowling ball was sitting there, and we threw a BB at it, and the BB bounced back off the bowling ball. So they had an experiment that clearly disproved that idea of the plum pudding. And so then Rutherford came up with what he called the planetary model. That, my friends, is the planetary model. The planetary model says that you have a nucleus where all the positive charge is, and then you have electrons orbiting it like planets orbiting the sun. Really quickly, they found problems with that. So within 2 years, it was relegated to the dust bin. Now, how many people here thought that was what an atom was? Only one?
Wait, that on the screen?
Yeah.
It's not.
No, that's not it.
Okay, then
Right, that's what most people think it is. But they realize that that's not possible. There's a lot of things that say that can't happen. One of the most serious of them is if you have a charged particle that changes direction, that's acceleration, it has to give off radiation and lose energy. So that the electrons would have to fall into the nucleus within about 1/1000th of a second if that was what was going on in atoms. There's some other things they discovered very quickly that are wrong with that model. And so we have now what we call the quantum model for the atom. And the quantum model says we don't know where the electrons are or what they're doing. We know they're not doing circles, but we know they have energy and they're moving out there, and that we say they're in a cloud. And we can't tell you where the electron is, but we can calculate where it's likely to be found if you study the atom and look for the electron. So our model, for what we really understand, instead of showing a circle, they usually show a fuzzy thing because we don't know where the electron is. We just know it's somewhere in there, or the multiple electrons. And we can calculate their most likely distance from the nucleus. We can calculate their energies, but that's all we can do. So I've talked about pretty much everything here, except for the difference in a conductor and an insulator. Everybody knows that if you have, I hope everybody knows, you may not have all grown up like I did, if you have an electric fence, if you touch it, what's going to happen? Get shocked. What if I take a nice piece of metal like this here, and I hold the metal and I touch it with that metal, what's going to happen? Still going to shock me. What if I hold the wooden handle and touch it with the metal? Doesn't shock me. There's a difference apparently between the way wood deals with electricity and the way metal deals with electricity. And so we call the metal a conductor. We call the wood an insulator. The difference between a conductor and an insulator is that in an insulator, these two things here were both insulators. Electrons are stuck. They can't move around. It takes energy to make the electrons move. So when I rubbed these, I moved electrons onto the insulators, but they were stuck there. And then when I touched them on this, I could rub them off of this onto that. With the conductor, metals are conductors, you have electrons that are actually free to move in this. It takes very little energy to make an electron move in a metal. And so if I touch this to something that has an electric charge, charge is going to move on this in response to it. So this has electrons that are free to move. The protons can never move. They're stuck. But electrons are free move, so I touch this to something that's negatively charged. Electrons are going to flow from that negatively charged thing onto this. If I touch to something that's positively charged, electrons from this are going to be pulled away and it's going to lose electrons. The insulator, if I touch it, just the point that touches could gain or lose electrons, but everything else will stay neutral. So that's the fundamental difference between conductors and insulators. And so we have electric cables. Well, this isn't truly an electric cable, but they always have an insulation on them. If this was a plug, like you have on the desk there, you plug that into the wall and you have a voltage. Voltage is the energy per charge that's going between plus 170 and minus 170 volts. We say it's 120 volts AC alternating current because it's going positive and negative. But the voltage is the energy that the charges have in that wire. And so that's going, everybody knows, 100 volts is going to shock you, right? But I don't worry about grabbing this because it has insulation around it so the charge can't pass through. So we use insulation to make sure we don't get shocked. Okay, I'm going to go right past this. We've talked about these things. Let's have our first clicker question. When you brush Fido's fur and scrape electrons from it, so that's just like doing this here with the amber rod, right? Fido's fur is this. Electrons leave Fido's fur. The charge of Fido's fur after I've done that is going to be hooray! Raquel, yours is registered now. At least it put it on your name. That's the first time it's ever done that. We'll see if I can upload them. Okay, waiting for Carmen and Valerie. Carmen? Is she working on it? Because this is probably the only, since we only have 5 minutes left, probably the only clicker question. I don't want you to get job. There we go. So we have 13 that said positive, 3 that said negative. Let's go to our woman in the field, Valerie, who's the only person who wasn't able to answer. I'll give you credit for this since you're being called on, Valerie. What's your answer?
My answer would be positive because the electrons are being brushed off, so the protons stay because they can't be removed, so the overall charge would be positive.
Okay, that's perfect. The protons can't move. She put that in there. So initially you had neutral, which means you have the same number of electrons as protons because they have the same magnitude of charge, just one's positive, one's negative. You take away the negatives, you keep all the positives, it's got to become positive. Very good. Okay, and this is, he's just a little more showman than I apparently. We've already seen Coulomb's law written out, and I've already talked to you about these two things. Remember, I just gave you more digits on both of them. I gave you 1.602 and 8.987 instead of 9.0. And I've even talked about this. It's a good thing I talked about all these things. This here is not actually a picture of an atom, although it looks like it is. It kind of is. This is supposed to be an atom with a positive nucleus, and then the negative charge is represented in this case by those dots. And the dots are telling us the probability of finding the electron there. So you can look and you can say, okay, Notice that the dots are a little stronger farther away from the center than they are at the center. We're more likely to find the electron somewhere in the ballpark. Okay, failed at the end. I was doing well for most of the circle. Somewhere in the ballpark of there is where we're most likely to find the electron. So in the naive picture that showed electrons doing a circle around the nucleus, that circle is showing the region where, or the path where it's most likely to be found, to try to make things easier to understand. Now, if I bring a positive charge and put that positive charge here, what's the positive charge going to do to the electrons? Attract them, because the electrons are negative. Positive charge, positive, opposites attract. And so that lower picture is showing what happens when you bring a positive charge nearby. It causes the charge to separate, so you have more positive now on the right side, more negative on the left side, because that negative charge was attracted to the positive charge I brought nearby. And so we call this electric polarization, or we say it has an electric dipole. Di means two, poles is talking about charges. So we have effectively the center of the negative charge is here, center of the positive charge is there. We have the dipole because they're separated. And that becomes important for things like playing with balloons. I didn't bring a balloon, which is fine because I also don't have time to play with the balloon. But you probably know, you take that balloon, you rub it on your hair, and then you bring it to the wall, and what does it do? It sticks to the wall. What happens when you rub the balloon on your hair?
You add.
If I can believe this picture, and Johnson, you're thinking the right things, okay? If I can believe this picture, electrons were pulled off of my hair onto the balloon. And so the balloon now has a negative charge. When I bring it to the wall, that negative charge is going to push away electrons, making the part of the wall that's closest to it a little bit positive. And because the force is stronger for closer things, you have an attractive force between the wall and the balloon now. Now there is a repulsive force between the electrons that got pushed away, but because they're farther away, that's going to be a weaker repulsive force, and that's why you can make the balloon stick to the wall.